from the book of real analysis by RG BARTLEY. Let us do our next result. So, theorem 2.1.9, as per theorem 2.1.9, if A is any real number such that 0 is less than equal to A is less than epsilon, for every epsilon greater than 0, then we need to show that A equal to 0. So, let me recall that to show that A equal to B using epsilon, we can call epsilon method for our sake of understanding, that for every epsilon greater than 0, if for every epsilon greater than 0, absolute value of A minus B is less than epsilon, where A and B are also real numbers, this implies A is equal to B. A is equal to B. So, if we recall the definition of absolute value function, then absolute value function always takes value either 0 or greater than 0. So, since this whole quantity has to be less than, and this cannot be negative because there is absolute value function. So, the only possibility is A minus B has to be 0, which implies A equal to B, and if we take B equal to 0 here, we will get this result. Or one can do it with the method of contradiction, which is mentioned here, that suppose if A belongs to R is such that 0 is less than equal to A is less than epsilon for every epsilon greater than 0. A has to be less than every epsilon positive, then the A is equal to 0. So, to do this, we can take, if we are able to discard that A greater than 0 is not possible, then here we have two choices, either A is greater than 0 or A is equal to 0. So, we need to discard this one. So, if A is greater than 0, then obviously A by 2 will be less than A y, because A is strictly greater than 0. So, now if I call this as epsilon or epsilon dash or epsilon naught, whatever notation, then we can see that this here it is given that A is strictly less than epsilon for every epsilon positive, where epsilon is any positive real number. So, if I call this one as epsilon, then this result that A is less than this condition is going to fail. So, we will get a contradiction. So, that's what written here, that if we choose epsilon naught equal to A by 2, then epsilon naught will become less than A. So, this restriction that the condition that A is less than epsilon for every epsilon greater than 0, we will get a contradiction. Hence, the only possibility is A equal to 0. So, this is one of the proof which we will use at several places. Now, next theorem. Yes. Let us do corollary 2.4.4. So, before doing this one, we can do this one using this one, Archimedean property of real numbers, Archimedean property of real numbers. For that, I need to recall the statement of Archimedean property of real numbers. So, let me recall this first. So, if you recall Archimedean property of real numbers, then as per statement of Archimedean property of real numbers, for every x y belonging to R, Archimedean property of real numbers, so I can write it as say Archimedean. In earlier classes already I have discussed all these things, Archimedean property of real numbers, property of set of reals. So, for as per Archimedean property of real numbers, for every x y belonging to R with x greater than 0, there exists at least one natural number such that n times x will exceed y, such that nx exceeds y. Since this relation is true for each y, whether y is negative 0 or y positive, the only condition restriction is on x. So, since this is true for each y, so this will be also true for y equal to 1. So, we can rewrite, or we can call its corollary, that for y is equal to 1, and in place of x let us take epsilon notation, which is strictly greater than 0. Then I can say that for every epsilon greater than 0 there exists n belonging to set of natural numbers such that n times epsilon is strictly greater than 1 or 1 by n is less than epsilon. So, this one is Archimedean corollary of Archimedean property of real number, Archimedean property of real numbers. We will use it in this proof. Now, let us do this statement. Let us do this 2.4.4 corollary part. Question is that if the here set is collection of all those elements of the type 1 by n, where n is coming from natural number, we need to show that its infimum is 0. So, one of the technique I have already discussed that for this set collection of all those 1 by n such that n belonging to n, clearly 0 is one of its lower bound, 0 is one of its lower bound. In fact, every real number less than 0 is also its lower bound, because 0 is less than equal to 1 by n for every n belonging to set of natural number, or I can write that 0 is less than equal to x for every x belonging to the set S. In fact, set of all lower bound, what will be set of all lower bounds? Set of all lower bounds of the set S is basically minus infinity to closed at 0, and as per definition, infimum of any set, here in case of set S, is defined as greatest lower bound. So, these are the collection of lower bounds. So, the greatest among them is 0. So, this is one of the technique, but let us do it using Archimedean property of real numbers or the result which we have just covered. Let us first do this using this argument that if A belongs to R and 0 is less than equal to A is less than epsilon for every epsilon positive, then A has to be 0. So, we can use directly this one also. Let us do it one by one. Now, since this set is non-empty because it contains element of the type 1 by n, and also this is bounded below by 0. So, all 0 is 1, that is one of its lower bound, and negative numbers will be discarded because we have a number greater than those negative numbers, say 0. So, the chances of infimum is either it is going to be 0 or any real number greater than 0. We need to discard that any number which is strictly greater than 0 cannot be its infimum. So, let us call its infimum as alpha W or alpha as infimum of this set, and infimum is guaranteed to exist. Why? Because this set is bounded below. So, from completeness property of real number, infimum will exist. Now, here we have two choices for alpha, that alpha is strictly greater than 0 or alpha is equal to 0, because already we have discarded alpha equal to negative will never be its upper bound, because we have elements which will exceed elements of the type 1 by n. Here alpha negative is also its lower bound, but the question is that we need to look at infimum, and infimum is greatest among all those upper bounds, all those lower bounds. Hence, we are getting alpha equal to 0 greater than those negative real numbers. This is the reason why we don't need to look at alpha is equal to negative, because we are getting here a bound greater than 0. Now, the possibility is that either alpha is equal to 0 as will be infimum, or alpha is strictly greater than 0. So, we need to discard this case. What we will do? So, see, since epsilon is greater than 0, so from Archimedean property of real number, there exists a natural number such that n times epsilon is greater than 1, or in fact 1 by n is less than epsilon. Look here, 1 by n is less than epsilon. This always we have from Archimedean property of real numbers, and this alpha is its lower bound because we have assumed it as infimum. So, infimum is also one of the lower bound. So, alpha has to be less than equal to each member of the set, and from Archimedean property 1 by n is less than epsilon. So, I will get this inequality that alpha is greater than equal to 0. If we combine these two conditions, alpha is greater than equal to 0 and less than equal to 1 by n, from because this one is a lower bound also, and 1 by n less than epsilon we are getting from Archimedean property of real numbers. Now, this inequality, if I compare this with the inequality which we have just done, this part, that whenever this condition is there, 0 is less than equal to a is less than epsilon, for every epsilon positive, then a has to be 0. So, using this condition, using this one, that is what here referred, theorem 2. Theorem 2.1.9. Theorem 2.1.9 implies that here I can write it as a is less than epsilon for every epsilon greater than 0, for every epsilon greater than 0. This is the reason why alpha is equal to 0 is the only possibility. So, alpha is equal to 0 here. Another reason we can use directly to counter this, that any real number greater than 0 cannot be its upper bound. Say suppose see alpha, we have condition here that alpha is infimum of the set S. This means this is also lower bound, this is also a lower bound. So, alpha has to be less than equal to 1 by n for every n belonging to n. Alpha has to be less than equal to 1 by n for every member of the set, and in case if alpha is greater than 0, suppose this one is also true, then from Archimedean property of real numbers, whenever alpha is greater than 0, just look here, whenever alpha is greater than 0, use this trick, whenever alpha is greater than 0 for every epsilon positive here, for every epsilon positive there exists n. So, whenever there is any real number strictly greater than 0, I can always apply Archimedean property of real numbers. So, from here there exists n belonging to set of natural numbers such that 1 by n is less than alpha. So, there exists at least one natural number, at least one real number of the type 1 by n, where 1 by n is coming from the set, this set S, which is less than alpha, whereas, so which is going to violate this condition. So, in this way one can also do that. We have a contradiction here directly using Archimedean property of real numbers. So, this is the technique we have done. Now, in density theorem there is one important corollary 2.4.6. Let me give you the basic idea of how to do this, because this one is a very important result, very basic result, that given any real number y which is strictly greater than 0, then there exists natural number say ny related to this y, or simply we can say n belonging to set of natural numbers such that n minus 1 is less than equal to y is less than equal to n. This we need to do using well ordering property. So, first of all recall the well ordering property. Well ordering property well ordering property of set of natural number, As per definition of well ordering property, every non-empty subset of natural number has a list element, So, since every set is subset of itself, so let us say start from set of natural number 1, 2, 3 and so on. Clearly its list element is 1 is the list element. Let us take any other finite set which is subset of natural number, say 2, 3 and 5. So, in this way we can check that this is going to be its list element 2. Any other set, say infinite set of subset of natural number, say 2, 4, 6, 8 and so on, then we can see that this is the list element. So, every non-empty subset of n has a list element. Now, how to do this using well ordering property? The Archimedean property ensures that the subset Ey, basically Ey is the collection of all those natural numbers which exceeds y, which is right to y. See, y is here, m is all those natural numbers which is right to y, and y is strictly greater than 0, y is strictly greater than 0. So, we are we have taken a subset Ey, collection of all those natural number which exceeds y. So, clearly this set is non-empty and also subset of m, because we are taking collection m from set of natural numbers satisfying this condition y less than m. So, by the well ordering property Ey, this set has a list element. Let us call those that list element as ny or simply n. Now, look here, let us take any of the case here. See, if ny is the list element, this 2 is the list element, and if we subtract 1 from this set, then it will not be a member of the set A. So, similarly, since ny is the list element of the set Ey, and if we subtract 1 from this number list element, so it does not belongs to Ey. It does not belongs to Ey means ny minus 1 has to be less than equal to y. Either it will be equal to y or it will be less than y. Why? Because if it belongs to set, then ny has to exceed y. So, this means we have this relation that ny minus 1 is less than equal to y is less than ny. So, this simple result we need to do by quoting well ordering property, and we will use it in the case of proving this density theorem.